Howdy, y'all. Today we're going to look at directional derivatives and gradients. So directional derivatives. Think back to the last couple videos you watched. And one of them we talked about first partial derivatives and how it kind of related back to what we know about the slope of a tangent line for one variable functions. Um, Namely that whenever I take the first partial derivative of a function with more than one variable, the independent variable that I differentiate with respect to gives me the axis that the tangent line whose slope I'm finding is parallel to. So if I find fx, remember that gives you the slope of the line parallel to the or tangent line parallel to the x-axis. Fy gives you the slope of the tangent line parallel to the y-axis. And z, yeah, yada yada, etc. Parallel to the z-axis. Directional derivatives are a way for us to actually find the equation of a tangent line that is parallel to any vector that we want. Yep. The notation for a directional derivative is like this, right? So u represents the vector whose what's it called? Represents a vector that the tangent line will be parallel to, and f of 2, 0 gives me the function I'm differentiating and the point where I'm differentiating. All right, so I need to, for one other thing I want to point out here. When we do the actual computation of a directional derivative, the vector that we are moving in the direction of should be a unit vector. In this case, they state that u is a unit vector, right? But that's not always the case. For example, in the next one, the vector that we're given is not actually a unit vector. The magnitude of that is not 1. So before we can actually do the process, we would have to make this into a unit vector. But we'll talk about that in the next example. So the way it works is that your directional derivative, again, is the slope of a tangent line. So the result is going to be a scalar, a number, right? That number is the slope of that line that's parallel to that vector. So the way that we get this number is by multiplying partial derivative times that component of the vector and then adding them. Basically, we're taking a dot product, right? So let's look at this example. So this is our function f of x, y. I'm going to need both of my first partial derivatives. So if I start with fx, remember x is the variable, y is a constant. So this term will have a derivative of 0. For this one, I have to use product rule. So derivative of x is 1 times e to the xy plus x times the derivative of exy, which in this case would be y e to the xy. And then, of course, derivative of y would be 0. Now to find the partial for y, again, x is a constant. Y is now a variable. So the derivative of this first term will not require the product rule, right? Because there's only one y, right? Only one of the factors involves the actual variable. So derivative for this would be x squared e to the xy. Remember, I'm just multiplying by the derivative of that exponent. And then for y, derivative of y with respect to y is 1. So now we have our partial derivatives. The next thing we need is to write out a unit vector. Okay, so the unit vector that we get is, so it says unit vector and then it gives us a direction. Remember when we have our, direction, we can write our vector out in component form by doing r cosine theta for the x component and r sine theta for the y component. Remember, r is the magnitude of the vector. In this case, because this is a unit vector, remember that means that the length of this vector would be 1. So I can write this in component form as 1 times cosine of 2 pi over 3 and 1 times sine of 2 pi over 3. And because we're unit circle masters, we know that this works out to negative 1/2 and positive square root 3 over 2. So now that we have both of our partial derivatives, no, there we go. Okay, now that we have both of our partial derivatives and our unit vector, we can get our directional derivative. And as I mentioned, it's essentially just taking a dot product. Right, before I do that though, I'm going to want to know what the actual values are for each of these partial derivatives. So, so we're going to plug 2, 0 into each partial derivative to figure that out. So if I plug 2 in for x, 0 in for y, this term will be e to the 0, which is 1. Then we have 2 times 0 times e to the 0, which altogether is going to be 0. So we know that the partial derivative with respect to x has a value of 1 at that point. Similar way, we can plug 2 in for x, 0 in for y to the partial with respect to y. So 2 squared times e to the 0. That would be 4 plus 1 gives me 5. So now I know that fx is 1 at this point and fy is 5 at this point. Now, essentially, my directional derivative, so du f of 2, 0, is going to be equal to a vector that is composed of the partial derivatives, so 1, 5, dot the unit vector that we wrote out here. Remember, whatever I take this dot product with, this one has to be a unit vector. This isn't going to be a unit vector usually, but the second one should always be a unit vector. So we'll put our points in. Okay, now when I take the dot product, remember you're just multiplying x times x plus y times y. So we get 1 times negative half plus 5 times root 3 over 2. Altogether, we get negative 1/2 plus 5 square root 3 over 2. And you could write that as a single fraction if you wanted, right? 5 root 3 minus 1 all over 2, right? But you don't have to. And this is a scalar quantity. Remember, this is a number, this is not a vector. And the meaning behind this number is it's the slope of a line that's tangent to that three-dimensional surface, but parallel to the vector u. All right, let's do one with 3 variables. So we want to find a directional derivative of f in the direction of u, right? Here we know that u is going to be a unit vector in the direction of the one that we're given here. So I can start by that, or I could start with the partials. It doesn't really matter. Remember, to make anything into a unit vector, all you have to do is divide each component by the magnitude. So magnitude for this one is going to be the square root of the sum of each of these things squared. So square that, you get 1, square that, you get 0, square that, you get 9. Add them together, you get 10. Take the square root, you get square root of 10. So we know that we're going to divide each component by the square root of 10. Now that we have our unit vector, we can go back and figure out our partial derivatives. So fx will have 2xz for the first term. Remember, anything that's not an x is a constant, so second term would have a derivative of 0. And the third term would be minus yz. Fy, remember now, anything that's not y is a constant. So the first term would be 0. Second term, 3y squared, z squared. And then the third term, minus xz. And finally, partial with respect to z. We would end up getting x squared for the first term, 2y cubed z for the second term, minus xy for the last term. So now that we have our partial derivatives, we can, well, we don't actually have a point to plug in. That just means that the answer that we get is going to be a function of x, y, and z. Meaning if I were given a coordinate to plug in for x, y, and z, the result would be a scalar value, right? Namely the w coordinate. So my directional derivative, I need some space for this one, right, is going to be equal to the dot product between this guy, which has a special name that we'll actually talk about in a little bit, dot, and then our unit vector. So first term we'll get negative 1 over root 10 times 2xz minus yz. Second term, we get fy multiplied by 0, which would just be 0, so we don't actually need that at all. And then for the last term, fz times 3 square root 10, so plus 3 over square root 10 times fz. That's a minus. There we go. And this is perfectly fine. If you have to simplify for multiple choice, the only thing you could really do is distribute, right? And if you have any like terms, meaning things that have same variables to the same powers, you can combine them. But yeah, so with that one, we ended up getting a function of x, y, and z. So again, if I'm given a coordinate that I want the directional derivative in this direction, all I have to do is plug in the x, the y, and the z, and I'll get the numerical value, right? The scalar quantity, the slope of the tangent line that is parallel to u. All right, now I mentioned that this guy had a special name. That name is gradient. Yep, the other major topic for this lesson. So a gradient is a vector quantity. So what we learned just now, what we did examples on, the directional derivative is a scalar. It's a number. The gradient is a vector. All right. And it actually has a lot of really cool, super useful qualities that we'll talk about after I show you how to find the gradient. So the gradient typically is noted using an upside down triangle, right? Called del. Yeah, although if you code in LaTeX, it uses a weird thing like nabla. Yeah, I don't know where that comes from, but it comes from somewhere. Anyway, so del is what's often referred to as the gradient operator. We may get into that a bit when we get to the last chapter. And if you take physics or engineering, you'll definitely see that all over the place. In fact, all of thermodynamics is based off of stuff that involves that. But I'm getting off track. Okay, so we represent the gradient with the upside down triangle called del. So we can write del f, right? X, y, and z are kind of implied there, but if you need to specify what the independent variables are, you can always write them out like so. And as I mentioned, this is going to be a vector. First component is fx, second component is fy, third component is fz. So these are all, the gradient is comprised completely of just first partial derivatives with respect to each of the variables in the function. The mustache is making me sneeze. All right, so fx, let's look at that. We get 2xz for the first term. There's no x here, so that's 0. Derivative of this would be just yz, so minus yz. Okay. The y component, and if you notice, this is actually the exact same function that we looked at in the last example. So I'm going to just copy pasta. Yeah, I'm just going to copy pasta these from what I wrote up here. So we get 3y squared z squared minus xz for our y component, and x squared plus 2y cubed z minus xy for our z component. And this vector is the gradient. You can, and if you are looking for the value of the gradient, well, I shouldn't say value, it's a vector, right? But if you are looking to figure out the gradient at a point, again, you would just be given x, y, and z coordinates that you could plug in to each of these components to get a numerical value for each component, right? So for example, if I were looking at the coordinate 0, 0, 0, all of these components would be 0. And the gradient would just be the 0 vector, which is pretty boring. All right. So I mentioned that there are some very useful qualities of the gradient. First, let me kind of explain generally, conceptually, what it tells us. So if you were on a point anywhere on a three-dimensional surface, the gradient is a vector that points you in the direction of the greatest rate of change. That can be a positive rate of change like a growth, or a negative rate of change like a decay or a decline, right? But the gradient will always point in the direction of the greatest rate of change. One common use that I use in real life whenever I go on vacation, it's that vacation. Um, is like if you're hiking on a mountain, right? If you're on any point on that mountain, right, the gradient would just point in the direction of the steepest ascent or descent, right? So if I'm starting to get off of the trail a little bit and I get to this really scary thing that looks kind of like a cliff, that cliff, right, straight down would be the direction that the gradient points because that's the steepest rate of change. Um, or if I'm going uphill, if you've ever been to Colorado and hiked some 14ers, you know that towards the end, when you get to the summit, you get to these points on the mountain where everything else is just a big giant hill that's nothing like the rest of the trail that you took to get there. So if you were climbing up that hill, right, the gradient would point in the direction of the biggest elevation change, be that a gain or a loss, right? I always say coming off the mountain is way harder than going up. But yeah, so the gradient points you in the direction of the greatest rate of change. If you find the magnitude of the gradient, then that gives you a numerical value for that rate of change. So it gives you the maximum rate of change. Like if I were to draw the steepest tangent line, what would its slope be? That is the magnitude of the gradient. Um, Other things is that the gradient is related to directional derivatives, which we already saw, right? Because I told you earlier that it's just this vector consisting of the first partial derivatives, dot product, the unit vector in the direction you're parallel to, right? So taking the dot product of the gradient and the vector you want to be parallel to gives you the directional derivative. Remember, the dot product is a scalar, which tracks because directional derivative is a scalar as well. All right. Other really interesting quality about the gradient is that the gradient is always perpendicular or orthogonal to a level curve at a point, right? So you remember your level curves, also known as your contour lines. We had our discussion about makeup. Yeah. But um, but remember those were the lines where all of the z coordinate, where every point on that line has the same z coordinate, right? Or w coordinate if you're looking at a hypersurface, right? Um, if you find the gradient and plug in the coordinates for the point that you're at, automatically you will get a vector that is orthogonal to that contour line. It's like you got your contour, the gradient would be poking out of your face and you would look like that dude from that horror movie. Yeah. Limited sleep. Okay. So let's look at some examples knowing what we know now. So we have the elevation of a hill is modeled by a function z equals all that. We're given a coordinate 60, 100. Going up the hill, give a vector that points in the direction of the steepest elevation gain. And then what is the steepest elevation gain at this point? So steepest elevation gain, right? That's asking us for the gradient. So a vector that points in the direction of the steepest rate of change, that's your gradient. And the steepest elevation gain or gain at that point is asking you for the magnitude of the gradient. So to start off, we'll write our notation, del z is equal to, and this is going to be a two-dimensional vector because there are two independent variables. All right, so first component will be the partial with respect to x. So that's 0. This will be negative 0.02 x, and that'll be 0. Now, partial with respect to y, 0, 0, negative 0.04 y. Okay, so at this point we have our gradient. Now if we use the coordinate that we're given, so we'll let 60 be x and 100 be y, we'll have the answer to our question. So we can write the notation del z evaluated at 60, 100. It's going to be equal to negative 0.02 times 60 and negative 0.04 times 100. Little number sense trick, it ends in a 0, which means I can move the decimal over 1. So I have 0.2 multiplied by 6, which would be 1.2. So negative 1.2. Another number sense trick, this one ends in two zeros, so I can move my decimal point 2 to the right. So negative 4. So this would be the vector that goes in the direction of the steepest elevation gain, right? Now to find the actual value of that rate, we would need to take the magnitude of the gradient of z evaluated at 6100. Since we already know the components, all we do is just our regular magnitude formula. So it'll be negative 1.2 squared plus negative 4 squared. Right, and number sense trick, 12 squared is 144. Each of these 12s has the decimal 1 to the left. So I would move my decimal 2 to the left from 144, and I would get 1.44. And then negative 4 squared, we get 16. So the answer would be the square root of 17.44, which has a numerical value that you can get from your scientific calculator. Okay, so the next example asks us to find the directional derivative, right, of this function f of xy using the gradient, which we've basically already done, but now we're going to write it in that form. So we know that directional derivative, so derivative in the direction of u of f evaluated at 2, 0 is going to be the dot product of del f evaluated at 2, 0 and the unit vector u. If I write those out, right, x direction, we said that fx, to remind ourselves, was equal to e to the xy plus xy e to the xy. So if I evaluate that at 2, 0, we get e to the 0, 1 plus 0 gives me 1. Also to remind ourselves, fy was equal to x squared e to the xy plus 1. If I plug those same coordinates in, I get 4 times 1 plus 1, so 5. So now I've got my gradient evaluated at that coordinate, 1, 5, and we're going to take the dot product of that with the vector u, which if you remember was cosine of 2 pi over 3 sine of 2 pi over 3. So that was minus 1/2 and square root of 3 over 2. So taking that dot product, we get negative 1/2 plus the square, 5 times the square root of 3 over 2. And there we go, same answer. So next one, we're given our function of 3 variables. We want to find a vector orthogonal to f at the point 1, 0, negative 2. And then we want to determine the maximum rate of change of f at that point. So a vector that's orthogonal to f at this point would be let's see. So the gradient, yep. So the gradient of f at this coordinate all right, we can get from taking our first partial derivatives. So we have, just to write them out here, 2xz minus yz. Then we've got for fy, 3y squared z squared minus xz. And for fz, all right, we've got x squared plus 2y cubed z minus xy, right? So this is one that we also looked at earlier. If I want to evaluate these at this point, all I need to do is plug in these values. 2 times 1 times negative 2 minus 0 times something, so just that. For fy, we would get, well, anything that has y in it as a factor is going to be 0. So that's 0. X times z would be -2. So minus -2 to me 2. All right. And then for the very last one, that's going to be a 0 term. That's going to be a 0 term. Right, so all we have is x squared, which is 1. So altogether, the vector that we get for our gradient is -4, 2, 1. And this would be orthogonal to a level curve on that surface. So it was a fancy way of just asking you to find the gradient. That's all it was. Now, to determine the maximum rate of change at this point, we would need to find the magnitude of del F evaluated at that point. So using my magnitude formula, I would get the square root of -4 squared plus 2 squared plus 1 squared. 16 plus 4 is 20. Add 1, you get 21. So our maximum rate of change would be the square root of 21. All right, and then we have another example. Sketch the level curve corresponding to c equals 0 for this given function, and find a normal vector at several points on the curve, then draw your normal vectors. So, first off, level curve. Remember the level curve, if you wanted to draw it, you would obtain by taking your function, so y minus sine of x, and setting it equal to whatever the constant is, right? So remember, they all have the same z coordinate. Here we want to know, here we want to set the function equal to z equals 0. So if I rearrange this, I end up getting y equals sine of x. That's a pretty easy contour line to draw with a pencil, not with a makeup brush. Not that I would know. All right, we end up drawing a sine wave. So remember, this one passes through the origin at pi over 2. We hit the max at a y coordinate of 1. And it's not pointy, it is a smooth wave. At pi, we come back to the x-axis. 3 pi over 2. We're down at the minimum value of -1. Remember, we want a smooth curve, not pointy vampire teeth. And then at 2 pi, we're starting over again. All right, and I could do something similar, negative pi over 2. We're at the bottom of the wave. Negative pi, we're crossing the x-axis again. -3 pi over 2, we're back at the top of the wave. And it goes down from there. Okay, so we have our sine wave. That's the level curve or contour line, right? We want to figure out what the normal vector is for several different points on the graph. So if I were to, if I were to find a normal vector, remember normal is the same thing as saying orthogonal, which is the same thing as saying perpendicular. So normal is the same as saying perpendicular. How do I find a vector that's normal to the contour line? I take the gradient. So del F for any point xy be a vector whose x component is the partial with respect to x. So that would be 0. This is negative cosine x. And y coordinate or y component is going to be the partial with respect to y. So 1, 0. So 1. That's our gradient. Now we want to find this vector at different values of x, y. So let's say I start over here at the origin. And here I'm just plotting points that are easy just to kind of see what it looks like on the level curve, right? This isn't something you would get like in the homework where you randomly just have to pick numbers yourself, right? But it's illustrative in nature. So if I let x be 0 and y be 0, this component will be -1. This component is going to be 1 no matter what x and y are. So if I start at my origin, I'm going to go to the left one, up one. That's going to be the terminal point. Then I draw my vector. And you see how if I were to draw a tangent line there, this would be perpendicular to that. There we go. Orthogonal at that point to the level curve. Okay, now if I pick an easy unit circle value, right? So I know I'm taking cosine. Yeah, I know I'm taking cosine of x. So if I let x be something with a clean value for cosine, or like a easy-ish value for cosine, I should use that. So I'm going to go with pi over 3. All right, and y doesn't actually matter because this vector doesn't actually depend on y at all. Like there are no y's in here, right? But if x were equal to pi over 3, y would be equal to sine of pi over 3, which would be the square root of 3 over 2. Right? Again, that's not going to affect anything. And the way I got that number is just by plugging into here, right? But if I do that, we get negative cosine of pi over 3, 1. And because we're unit circle rock stars, we know that cosine of pi over 3 is a half. So negative half, comma 1. So let's say I'm at the point on the contour line that corresponds to pi over 3. So you have pi over 6, pi over 4, pi over 3. It's going to be this point. From there, I'm going to go down a half, or no, not down, left a half. So almost back to the origin, and then up 1. Well, let's see. It's pi over 3. Yep. So it'd be about right there. And if you look at that, there we go. And I'll do one more to illustrate this. Let's say I choose pi over 2 as my x. Sine of pi over 2 would be 1, so the y would be 1 on the contour line. My vector would be negative cosine of pi over 2, which is 0, and then 1. So if I'm starting at the point pi over 2, 1, I'm going to go over 0 units and up 1 unit. And there we go. So for each of these, God, I cannot draw a straight line to save my life, especially in June. There we go. Okay, so you can tell that all of these vectors that we've drawn are perpendicular to what our tangent line would look like at each point. Right? So like here we would have a flat tangent line. Clearly that's a 90-degree angle. Here our tangent line would have a relatively small positive slope, and that would be a right angle. That has a steeper slope, and again, that's a right angle. So there we go. We can use the gradient to find those perpendicular vectors. All right, one more concept for part 3 of chapter 13. Tangent lines and normal planes. Okay, or I said that backwards. Tangent planes and normal lines. So if I have a three-dimensional surface, right? Just as we have tangent lines on regular curves, we can actually have tangent planes on three-dimensional surfaces. right? You think of it as like supermaning the surface, the three-dimensional surface. It's like you're flying and you touch the surface at exactly one point, right? I could even draw that. That should have been an illustration in here. All right, but we can find the tangent plane or even a normal line for a three-dimensional surface. And again, that would be where you have a line that's poking directly out of the surface, making a 90-degree angle with the tangent plane or any tangent line, right? And basically we can use the, yeah, and basically we can use the gradient to kind of figure out what these different things are. So the first example, we have the equation for a hyperboloid, and we have a point. We want to find both the tangent plane and the normal line. So we'll start off by calculating the, yep. So we'll start off by calculating the gradient of z, or no, f, the gradient of f. Yeah. So we're finding the gradient of basically this entire left-hand side. Key thing I want to say before we get into it is that you want your right-hand side technically to be zero, but if it's a constant and just a constant, that's also fine. Because if I take any partial derivative, the constant would be zero. So in the textbook, they refer to this as capital F of XYZ, right? Um, and so we'll label that over here, capital F of XYZ. So if I take the gradient of this, the result is a three-dimensional vector. X component would be the partial with respect to X. So that's 0, minus 4X, and 0. Okay, and then second component is the partial with respect to Y, 0, 0, minus 4Y. And then the third component is our Z component, partial with respect to Z. So 2Z, 0, 0. And now that we have the gradient, we can actually use this to come up with an equation for the tangent plane. So if I plug in the point that we're given, oops, we get that del capital F evaluated at this point is equal to -4 times 1, -4 times -1, and 2 times 4. So if you remember back in chapter 11, we learned that to find an equation of a normal line to a plane. So like if I have a plane and I want the equation of a line that is sticking out like this, right? I need to know two things. I need to know a point and I need to know the direction numbers, which can be obtained either from a vector that is parallel or a plane that is perpendicular. So in this case, I have a normal line, or no, I have a gradient which is normal to a level curve, so normal to the surface. And um, and I want a tangent plane, right? Normal and tangent are perpendicular, right? That's a line or vector, that's a plane. So I can use these as the slopes for some of the parts that come up in my equation. And then the y-intercepts we can use as these points, okay? So I know in the x direction, the slope was or the direction number was -4. So I would start with -4 times x minus the x coordinate. Direction number +4 times y minus the y coordinate. Plus direction number times z minus the z coordinate, right? And that would be equal to 0. Yep. Sleepy. All right. So this is an equation for the plane. Again, if you were to distribute combine like terms, you would get an answer that looks slightly different, but is mathematically equivalent to this. So now that we've got our tangent plane, let's write an equation for the normal line. So the normal line would pretty much go the exact same way. Well, we would write it as a vector valued function, right? So remember with these vector valued functions, each of these would be a parametric equation, right? Each of your components. So rather than having something in terms of x, y, and z, everything will be in terms of our parameter t, right? Again, this is a throwback to chapter 11. So slope is going to be our direction number that we get from the gradient, and the y-intercept is going to be the point. So for the x component, right, we would get 1 minus 4t. For the y component, we would get -1 plus 4t. And then for the z component, 4 plus 8t. And that would be our, what's it called? Equation for our normal line, which we could write as n of t. Okay, so the next one, we want to find a set of symmetric equations for the normal line to the surface xyz equals 12, and then they give us a point. So again, as long as the right-hand side is a constant and only a constant, or just 0, we don't really need to do any rearranging. With that said, our capital F of x, y, and z this time is just the left-hand side, x, y, z. Right? If I find the gradient, del f, just in general, x component would be yz, right? That's the derivative of this if y and z are constants and x is the variable. Right? Y component xz and z component xy. So we've got our gradient. Now I want to find that gradient at the point to get my direction numbers. All right, so we end up with plugging in the point 2, -2, -3. There we go. For our x component, -2 times -3, so we get 6. For our y component, x times z, 2 times -3, we get -6, and x times y, we get -4. So this gives us our direction numbers, which remember are going to serve as the slopes in our parametric equations. So this does say to write symmetric equations. Remember, all that means is that we have to solve for t and set everything equal to each other, right? But to start off, we're just going to write parametric equations. So x is going to be equal to my x coordinate plus 6t. Y is going to be equal to my y coordinate, -2, minus 6t. And then z will be my z coordinate, -3, minus 4t. And these are parametric equations. Technically, this does describe the normal line, right? But to answer the question in the way that we were told, right, we would need to basically just solve each of these equations for t and then set the results equal to each other. And those would be your symmetric equations. So for x, I would subtract 2, so I have x minus 2, and I would divide by 6. For y, I would add 2, and I would divide by -6. And for z, I would add 3, and I would divide by -4. And those are my symmetric equations.